Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leader series, Innovation in Post-Installed Rebar Design. My name is Megan Purdy and I'll be your host for today. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodian of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them and their cultures and to elders past, present and emerging. Before we get started, I would like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, Hilti. Hilti is a world leader in the design and manufacture of cutting-edge technologies, software and services for the professional construction industry. Hilti engineers and technical specialists have lived at the forefront of construction. They've helped make job sites safer, more productive and more advanced. Hilti Engineering Solutions have set the standard for excellence, offering a range of technical solutions, services and software to help you take control of your project from the initial design brief through conceptual detailing to final product selection and installation. Now today, we'll hear from two speakers followed by our live audience Q&A, and I encourage you all to please send your questions through to our speakers via the chat box. I'd now like to welcome our first speaker, Baz Kaknix. Baz holds a Master of Science in Civil and Structural Engineering and has been working in various technical roles related to fastening technology for over 17 years. He is currently the Codes and Approvals Manager for Anchors at Hilti Australia and also a member of the Board and Technical Committee of the Australian Engineered Anchors and Fasteners Council, AFEC. In 2020, he joined the working group under the ME029 Committee of Standards Australia to contribute to the revision of the AS 5216. Please join me in welcoming Baz Kaknix.
Thank you very much for the introduction, Megan. It's a pleasure to be part of this collaboration with Engineers Australia. In the first part of today's webinar, I will be presenting about selecting the right design approach for post-installed rebar connections. But before we get into the design topics, let's start with the definition of post-installed rebar. The intention of installing bonded bars is to develop a monolithic connection between new and existing concrete elements, which we often refer to as concrete-to-concrete connections. This is achieved by drilling a hole into the existing concrete, which is then injected with a pre-qualified high-strength usually special type of epoxy or vinyl ester product. After this, a cut-to-length reinforcing bar is inserted and left alone until the chemical is fully cured. The surface of the existing concrete is often roughened to improve the transfer of shear stresses between the new and old concrete. And finally, the new concrete is poured, turning the two structures into one monolithic unit. To better understand the applications in question, let's go through some real-life examples of post-installed rebar connections. Here in this slide, you can see some examples for connecting new slabs to walls, a balcony extension, closing openings or enlarging existing slabs, or for example, a staircase connection. Then some further examples include attaching new columns to a foundation or extending existing ones, bridge enlargements, beam connections and post-installed corbels, or connecting reinforced concrete walls. And finally, some examples for rectification works on site. For example, when there are cast-in bars or ferrules missing, or there is a design requirement for the addition of more rebar. One of the biggest challenges we see designers face is designing post-installed rebar connections correctly. Actually, there is little awareness out there about the existence of various design methods, and today's webinar is meant to cater for exactly that issue. Therefore, in the first part of the webinar, we will investigate how post-installed rebar design differs from post-fix anchors and exactly what design methods should be chosen for your given application. So in order to understand the differences between the behavior of post-installed rebar and anchors, I like to take you back to the very basic principles and re-examine what exactly happens when we install an anchoring element into the concrete and put it under load. By doing this exercise, by the end, you'll understand some of the seemingly subtle, however very important differences between the two applications, which finally warranted the development of different design and qualification methods. Based on these learnings, then you will be able to select the correct design method, which is best suited for your application. So first, let's investigate the basic working mechanisms of any anchor or rebar bonded into concrete-based material. So this is our concrete, and this is our post-installed rebar in this case. Let's assume that the embedment depth is relatively shallow here, and we are using a very high-strength epoxy mortar, which will provide us with a strong bond into the concrete. Then, as we exert some tension force onto the bar, which the bar then transfers over the concrete via adhesive bond and friction, this will create stresses in the base material around the fastening. Amongst those stresses, there will be tensile stresses, and we know that the concrete's tensile capacity is quite limited compared to its high compressive strength. So sooner or later, we will reach the ultimate limit state where the concrete cracks under tension. These cracks quickly progress into an abrupt failure called concrete cone breakout, and ultimately our connection fails. And here you can see the typical shape and form of the concrete cone. After decades of research and tens of thousands of destructive anchor tests, the experts found that the concrete cone actually has a typical shape for the common concrete strength classes, which is characterized by an approximately 34-degree side angle, or with other words, this corresponds to a 1 to 1.5 depth to radius ratio. Based on the existing data, the scientists were able to find a mathematical formula to quantify the concrete cone resistance, which, as you can see, is relatively a simple function of the concrete strength and the embedment depth. Note that the cone capacity is directly proportionate to the concrete's tensile strength, which here is expressed as the square root of the compression strength. And more importantly, there is an exponential function relative to the embedment depth, which means that selecting a deeper anchorage length will result in a significantly improved cone capacity. So to sum it up, the most basic failure mechanism is concrete cone breakout, which is an abrupt, brittle failure mode. Brittle failure modes and the utilization of the concrete's tensile strengths are generally not supported in reinforced concrete design theory. For example, in our AS3600 standard, which covers the design of concrete structures. But it is also true that most concrete-to-concrete connections typically involve long enough anchorage lengths so that the cone breakout is unlikely to be the governing design case. So that being said, we will still have to live with the possibility of this failure mode in most anchoring applications, where, for example, we don't always have the luxury to select a deeper anchorage length or to directly transfer the tensile stresses onto an existing rebar, or perhaps to have any other measures in place which could hinder the formation of the concrete cone. Therefore, Section 6 of the AS5216, which is our design standard for post-installed anchors, mandates necessary strength checks against this failure mode. In summary, the utilization of the base material's tensile strengths and the handling of the concrete cone failure is the first major difference between anchor and rebar design theories. And if we were to plot the development of the concrete cone capacity based on the increasing embedment depth, we would end up having a nice parabolic function. As I said earlier, by selecting a deeper anchorage length, the resistance against cone breakout will improve exponentially. So let's see what other potential failure modes we need to investigate to better understand the differences between anchor and rebar design. Here we have a post-installed rebar bonded into the concrete at a medium depth embedment. As we load this bar up, more and more of the chemical's bond strengths will be utilized. And at the beginning of the loading phase, there will be more stresses transferred closer to the surface of the concrete. But as we increase the load and progress closer to the ultimate limit state, the bond stresses will start to become more even along the anchorage length, as you can see here. This happens right until we reach the ultimate limit state. And at this point, we will experience a drop in the maximum load along with increasing anchor displacements. With other words, a pullout or bond failure happens. Multiple studies have verified that up to an embedment depth of approximately 20 times the bar diameter, which is 20D, the bond stress may be assumed uniform along the entire anchorage length in the ultimate limit state. In case of a pure pullout failure, The mathematical formula is again very simple. Tau here represents the chemical bond strength, which we simply need to multiply with the cylindrical bond surface area in order to calculate the anchor's pull-out resistance. In the relevant Australian design standards, the formulas might look different to the simplified equation shown here. This is because, for example, AS5216 accounts for the potential combination of two failure modes instead of one, namely a combined cone and pull-out failure. AS3600, on the other hand, for the design of cast-in bars, is combining the pull-out with a potential splitting failure, which could limit the development of the full bond strength in case there is not adequate concrete cover surrounding the bars. Regardless of the different approaches in the various design standards, the basic principles of bond failure are still valid here, and an important takeaway is that the uniform stress distribution only holds true up to an embedment depth of 20D. This fact again might necessitate a different design approach for post-installed rebars versus anchors. Let's go back to our diagram and include the bond failure that we just discussed. As we said, the linear function will be valid up to 20D embedment, beyond which the efficiency of the bond slightly decreases. Now, in a similar fashion to AS3600, it is important to account for a potential splitting failure for situations where the concrete cover is limited, for example, small bar spacing or small edge distances. In case the splitting failure would occur before the bond strength could be developed, then we obviously won't be able to reach the full bond capacity of the anchors. And finally, the last failure mode I will look into today is basically the ideal outcome for most designs, which is the full development of the reinforcing bar, with other words, being able to reach full yield or steel failure. It is probably not necessary to explain the mechanisms of this failure mode. It's well predictable by a relatively simple and reliable formula. One of the main benefits of fully developing the bars is to be able to utilize the bar's ductile reserves to achieve more ductility in the design. Also, by designing to the full yield of the reinforcement, the use of materials in a structure can be optimized, minimizing the overall costs as well as the carbon footprint of the build. As our diagram is becoming complete now, it's quite evident that different applications might be restricted by different boundary conditions, which may result in different governing failure modes. In order to be able to achieve an optimal design, all failure modes need to be accounted for. And in the case of post-installed reinforcement, for example, the designer's main goal always should be to achieve the full development of the bonded bars. In practice, this means finding an adequate embedment depth and concrete cover so that the connection won't be restricted by brittle failure modes like concrete cone failure or bond failure and bar pull-out. In summary, the main goal of my presentation today was to help understand the differences between the anchor and rebar design theories. In certain cases, rebars may be designed based on the principles of anchor theory, for example, when they are used as shear keys or dowels, and the embedment depth is not greater than 20D, as we discussed earlier. Designers might also use this design method for shallow embedded starter bars, where concrete cone failure is expected and therefore must be accounted for. For the more traditional applications of post-installed rebar, however, the specifically developed rebar design methods should be utilized. These are suitable and safe to be used for deeper embedment depth, but the bars must only take tension forces, and the shear force must be transferred by different ways, for example, by roughening the concrete interface. In case the design method does not allow for the direct transfer of tensile stresses into the base material, for example, when using AS3600, then lap splicing must be utilized, or the bars must be anchored within the compression zone of the structure. A couple of application examples for using rebar design method, for example, typical concrete-to-concrete connections, slab extensions, wall-to-slab, wall-to-beam connections, and various rectification works, as we showed at the beginning of the presentation. Now that we differentiated the rebar from traditional anchor applications, I believe it's important to go through and summarize the different design methods which currently coexist in our code landscape. As shown in this slide, there are three different approaches for designing post-installed rebar, and each situation should be assessed correctly by the designer so that the most suitable design method can be chosen. The first one on the left-hand side, which means designing the rebar as an anchor, often relates to dowels or shear key applications. The qualification is according to the EAD document ending with 499, and upon successful assessment, the chemical gets awarded with an ETA technical approval, such as the one referenced here. The design method is according to AS 5216, section 6 and 7, just like in the case of normal anchors under combined tension and shear loading. The second option in the middle follows the common principles of reinforced concrete design theory, and the bars will be designed identical to cast-in bars based on the principles of AS 3600. This method will cover common structural rebar connections where the development length is typically longer than 20D and the shear force is not directly transferred by the bars. The chemical here will require a special qualification report, which is based on the assessment document ending with 087. This method doesn't utilize the tensile capacity of the base, and the tensile stresses will have to be transferred either via lap splicing with an existing bar, or the area of the bars, the area of the fixings must be under constant compression so that to rule out the possibility of a concrete cone failure. The third option on the right is a relatively new design method, which combines the benefits of the previous two. This will again require a third-party technical approval and qualification, and the performance of the bars may be higher than that of cast-in bars. This new method utilizes an improved bond splitting model, which is very important to emphasize. It differs by product to product, so it's product dependent, and it will be explained in a greater detail during the second part of this webinar. For the sake of completeness, this slide just summarizes all the potential localized failure modes for the aforementioned design methods. And as you can see, some of these failure modes are similar in case of both post-installed rebar and anchor applications, but the formulas might differ slightly due to the different characteristics of the fasteners, as we discussed before. And some of the failure modes, like the ones for shear on the right-hand side, are unique to anchor design only. For example, the shear force is directly taken up by the anchors, and it can affect both the steel strengths, and there could be concrete failures happening, for example, when the anchorage and the base plate is located close to the edge of the slab. Just another word of caution, that the failure modes discussed here today are all considered as local failure modes, which may develop as a direct result of the interaction between the fastening and the base material. The designer should, of course, never forget to ensure that the design actions introduced by the anchors can be safely taken up by the concrete structure, and there is adequate load path for the safe transmission of these additional forces down to the foundation of the structure. For example, it must be verified that the structure has adequate shear strength and existing or supplementary reinforcement to safely transfer the stresses away from the anchorage. To better understand the requirements for a concrete structure to accommodate the anchor forces, I would recommend to check out and follow the specifications of Appendix C within the AS 5216 standard. With that, my presentation concludes, but please stick around, as in the second part of the webinar, Dr. Tilak Pokharel from AFEC will provide you with an in-depth explanation of the design procedure utilizing the latest international and local guidelines. Thank you very much for your attention.
Thank you, Baz, for your input today. I'd now like to welcome our second speaker, Talat Pokharel. Dr. Talat Pokharel is the National Technical Manager of AFAC at Swinburne University of Technology. He holds a PhD from the University of Melbourne and a master's degree from the University of Tokyo. He has about 15 years of industry experience as an earthquake and structural engineer. His research focuses on finite element modelling, steel and composite construction, anchorage, and earthquake-resistant design. He is a Standard Development Committee member and the drafting leader for AS 5216-2021. He is also a member of the FIB TG 2.9 Fastenings to Structural, Concrete and Masonry. Please join me in welcoming Tilak Pokharel.
Thank you, Megan, for the introduction. In next half an hour or so, I'll be talking about few innovations in post-installed rebar connection design. So in this presentation, I'll be talking about the post-installed reinforcing bar and innovations in past a few years. So I will start with the brief introduction to AFAC and then provide you with a basic information of post-installed rebar connections and how they are different from other chemical anchors. I will then explain why and how they are different from the usual chemical anchors, followed by the pre-qualification and design requirements of post-install rebar connection in Australian standard AS 5216, and I will highlight some of the limitations of the method we have currently available in the standard. Then I will talk about the new developments in post-installed rebar connection and the utilization of that newly developed design method in designing post-installed rebar connections in Australia. And finally, I will conclude my presentation by providing some guidelines or suggestions on selecting proper design method and brief comparison of different design methods we have available in Australia. So I would like to start this presentation with these three critical elements that are very important to ensure the quality assurance of anchors. This presentation will be focusing on basically those three elements. The first one is pre-qualification. The anchor product must be independently tested and assessed to be fit for purpose. For example, if you are using the anchors that are used in the post-install rebar applications, they must undergo with a separate and unique type of testing and assessment with reinforcing bar to meet the requirements. And the second one is design. Robust design is required to ensure all possible failure modes are considered, and design is done by considering all those failure modes and identifying the critical failure modes. And finally, the installation. Installation is usually the weak link in anchorage industry. There have been many failures occurred in Australia and globally in the past because of the poor installation practice. So all these three elements are key for the quality of the connections. So for those who do not know about AFAC, AFAC stands for Australian Engineered Fasteners and Anchors Council. It is a non-for-profit industry initiative. It was founded in 2012 by Swinburne University and 6 other industry partners. You can see the name in the screen: DeWalt, Hilti, Hobson, Leviat, Ramsett, and Woods, to introduce the governance to the anchor industry based on the three critical elements for quality assurance of anchors that I introduced you in the previous slides. And AFAC has since grown. There are currently 13 members contributing to the work done by AFAC. Okay, AFAC contributes to various sectors in the anchor industry to uplift safety, quality, and efficiency. AFAC provides guidelines for design and specification of anchors for designers and for contractors. It provides training and certification for installation of anchors. AFAC prepares guidelines for field testing of anchors. It provides guidelines on the minimum performance requirement for anchor in safety critical application. And finally, AFAC does lots of research and development. At Swinburne, R&D is taking in various research areas such as anchor performance in oil-less concrete, seismic performance of fasteners, post-install reinforcing bar connection, and other type of innovative connections and innovative concrete. So before I move into the post-install rebar part, AFAC has several technical publications, including technical notes that you can see in the screen. And if you are interested in any of those, they are freely available to download on AFAC website, afac.org.au. Now let's come back to the post-install rebar. Okay, Let's look at the definition of PIR and chemical anchors that are currently used in Australian standard AS 5216. Okay, AS 5216 2021 defines post-install rebar as the reinforcement that is anchored into mature concrete using adhesive in drilled hole. And the standards defines chemical fasteners as the post-install fasteners that includes a steel element. The steel element could be a threaded rod or reinforcing bar, and a bonding compound that transmits load from the embedded steel element into the base material, which is concrete. Okay, they are also known as bonded fasteners or adhesive fasteners, depending on where you are. There are some overlaps between PIR and chemical fasteners, as you have seen in the definition. Thus, some designers confuse between the chemical fasteners and post-install rebar fasteners. The previous speaker has already defined the differences between those anchors, and I'll go a little bit deeper into that. And hopefully by the end of this presentation, it will be clear that there is a clear distinction between those two types of fasteners. And I believe that will help to avoid those confusions. Okay, as has already defined what are post-install rebar, but for the completeness, or if you have missed that part, I would reiterate that again. Okay, post-installed rebar is the rebar that is installed after the concrete has been poured and cured, usually after 28 days of concrete casting. Okay, once the concrete is hardened, a right size hole is drilled at required location. After the hole is cleaned as per the manufacturer's installation instruction for that chemical being used in the applications, the chemical or adhesive is filled into the hole, usually 2/3, and then reinforcing bar is inserted. So it is very important to note that the post-install reinforcing bar is only designed to take tension force. Okay, no shear force is taken up by the reinforcement. So new concrete is poured on the exposed part, and it is very common to make the surface rough before pouring the new concrete, as the shear force will be resisted by this interface. In Australia, we have Australian Standard AS 5216, and the recent edition is 2021 for the pre-qualification and design requirements for post-install fasteners and cast-in fasteners. That standard covers the chemical fasteners as well as PIR, post-install reinforcing bar connections. This recent edition, 2021, covers PIR in Appendix D. In this presentation, I'll not go into the detail of the design model and design process we have in the standard. Rather, I'll focus on the concept and more about the limitation and the scope of that method. And I will highlight why the new method is important and what is improved in the new design model. The design model we have in the current standard is referred as a current rebar model in this presentation. Okay, for the new model, I'll be using a new rebar model, which I'll introduce in the next couple of slides later. And I want you to take a note that the design method we have in AS 5216 2021 Appendix D is exactly same as the design model we have in AFAC Technical Note 8, Volume 1. So before looking into the post-install reinforcing bar in detail, let's briefly look into the design of chemical fasteners in tension in accordance with AS 5216. Okay, as Baz has introduced, we need to consider different failure modes, and we need to find the minimum value for that as design capacity or the tensile capacity of fasteners. There could be different failure mode, steel failure, concrete cone failure, pull-out failure, or the combination of pull-out and concrete cone failure, concrete splitting, and could be more if you are using supplementary rebar or something. Okay, you need to define or verify each failure mode and identify the critical one, and that will govern the design strength or the design capacity of the fasteners. This is the fundamental concept AS5216 is based on, and sometimes referred as CC method, concrete capacity design method. Okay. There are some limitations in terms of diameter and embedment depth of the fasteners. In this presentation, I will highlight the limitation in terms of depth because this is important for the post-installed reinforcing bar connections. If the fasteners, chemical fasteners, is less than 20 times the diameter of the anchor, then the anchor model or AS5216 can be used, chapter 6, 7, and 8. So that design process will include the verification of 5 or 6 failure mode I included in the previous slide. Okay, this design model we have is referred as anchor model in this presentation. Okay, this anchor model can be used for threaded rod as well as post-install reinforcing bars. Okay, but it is important to note that the scope of the pre-qualification document should clearly say that this chemical or this application is safe with reinforcing bars. And this is referred as anchor model, as I mentioned earlier. So it is assumed that in 5216 assumes that the bond strength is uniform throughout the embedded length of the anchor. The previous speaker has clearly explained that, and this assumption or this concept is called uniform bond stress model. And this is true for shallow embedments. Okay, the uniform bond model will be applicable to the shallow embedments. It has been tested extensively in Australia and in Europe and other countries for 8 to 10 times the diameter of the anchor. And it has been proved to work well if the embedment depth is about 20 times the diameter of anchor. And this is the reason why there is a limit in the maximum embedment depth of the anchor in anchor model. So as you expect, this uniform bond stress model does not apply to the anchor with deep embedment in reinforcing bar applications. So we cannot use this anchor model from AS5216 to calculate the pull-out capacity of the long post-installed rebar, which is more than 20 times the diameter of the anchor. Then what are the options? Okay, there are a couple of options available, fortunately. One option could be using the well-established AS3600 standards, the concrete standard, to calculate the development length. And that development length can be used as the anchorage length in post-install rebar application. This is only possible if we have some evidence that proves the post-install reinforcing bar works at least similar or better than the cast and rebar. Okay, this is very important because the presence of extra layer of chemical between the reinforcing bar and concrete could alter the performance of the system. Also, the overall behavior of the connection depends on the chemical, its strength, stiffness, and other parameters. So this is again obviously outside the scope of AS3600. So if you have the fasteners that has the pre-qualification report such as ETA that proves that PIR works at least similar to equivalent casting application, then the embedded length of the post-install reinforcing bar is equal to or longer than the development length. Rebar would yield, or there would be steel failure, rebar failure in tension would occur, and we can use that principle in designing the post-install reinforcing bar. Okay. This model is included in AS5216 and FAQ technical note 8 volume 1, and this is referred as current rebar model in this presentation. I'll be referring this method as the rebar model current in future slides. So the question is there any alternative to the current model which would utilize the better bond behavior of chemicals and design is less conservative than the current model? The answer is yes. There is a better alternative design model available, which I will be talking about in next few slides. And this model is referred as Rebar model new in future slides. Okay, so the current Rebar model, there are some limitations. So before I talk into the limitations, let's look briefly at what are the major limitations and what is the design concept there. So AS3600 is used to calculate the development length, as I mentioned earlier, and use that development length as anchorage length in current Rebar model. And to demonstrate the comparable performance of the PIR to cast-in solutions, we need to do a test according to Appendix A of AS5216, which refers to EAD 330087. That means if you have the PIR system, post-install reinforcing bar system, that has passed the test and assessment in accordance with EAD 330087, which you can see in the screen there, it is proved that the PIR works at least similar or better than cast and rebar, so that you can use AS3600 design principle, section 13 of AS 3600. It is very important to note here that even if it is proved that the post-install reinforcing bar works better than cast and rebar, this standard does not allow to utilize the better performance of PR. So in other words, this is pass-fail approach. That is, if the bond strength of the post-install reinforcing bar is higher than that of the cast and rebar, we still have to use the bond strength of cast and rebar. Okay, so I'll explain this with number in next slide. Yeah, here it is. So this is the table I took from the pre-qualification document EAD 330087. I put this table here to show how the design bond strength is determined in that pre-qualification method. Okay, there are three parameters in this table. The first one is nominal compressive strength of the concrete. And the second parameter is the required mean bond resistance for post-install reinforcing bar in assessment is equivalent to cast and rebar. That means if the bond strength is equal to that value, then we can utilize the FBD PIR value, which is the third parameter. The design value of bond strength of PIR is used in design. Okay, it has different numbers there. For the simplicity, let's pick one concrete grade and look into the detail. Here, I've chosen the 20 megapascal concrete as highlighted in green in the screen. The bond strength of the post-install reinforcing bar is calculated from the experiment in accordance with EAD I mentioned earlier. So if the bond strength from the experiment is higher than 10 megapascal, the design bond strength is taken as 2.3 megapascal. Okay, so if the test value is 10 megapascal, design value would be 2.3. So there is a large safety margin here. Okay, in the pre-qualification method we have in AS5216 or in the current rebar design model, it does not matter how large the bond strength from the experiment is. It doesn't matter whether it is 10 or 20 or 30 or 40. The design bond strength is 2.3. Okay, and we use the chapter 13 of AS 3600 to get the development length as anchorage length. Okay, so what is the issue here then? So the bond strength of chemicals we use in connecting post-install rebar have significantly higher bond strength than the cast-in equivalent. Okay, but as we just saw, the current rebar model does not utilize the higher bond strength. The limitations on the AS5216 was put to prevent the slip of rebar under the serviceable conditions, to avoid the splitting of the concrete, and to address the uncertainty of the unequal distribution of the bond strength over the embedded length. Okay, thus if we have some new model that address the slip under the serviceability load, splitting of the concrete, and the variation in stress distribution along the length of the rebar, we could utilize the higher bond strength of the post-installed rebar system. So why it is important? Why it is important to take the better or the more realistic bond behavior of PR system? to understand this, let's look at the effect of bond strength, why bond strength is important in overall behavior of post-install reinforcing bar connection. The bond behavior typically has two aspects, okay, namely bond pull-out and concrete splitting. The splitting behavior of concrete is dependent on parameters such as concrete cover, concrete strength, confining reinforcement, diameter, geometry of the rebar, spacing, pressure, and so on. Okay, there are so many parameters that affect the splitting of the concrete. So to understand it more clearly, with all parameters being same, the bond splitting strength will increase with increasing the concrete cover. Okay, and this increase in behavior is there until it is capped by the bond pull-out strength. This behavior was shown very clearly in the graph by the previous presenter. However, currently, these aspects are not considered while recommending the design bond strength values for PIR. AS5216 or the current model requires the test to be performed using confined tension test setup. Confined test setup is used to prevent the concrete cone failure. This requires relatively large cover to prevent concrete splitting. Okay, these conditions may not replicate the boundary conditions available in real construction or the real applications. For example, in the case of extension of thin slab or connection to small beam or small column. In the real conditions, the rebar is often provided with small cover and the bonded segment is subjected to tension force in unconfined manner. That means there is a possibility of concrete splitting and the pull out in there. So since the actual bond strength of post-install reinforcing bar could be rather high, so under realistic boundary condition, concrete splitting would often govern the failure prior to pull out of the rebar. Therefore, to understand the behavior of a post-install reinforcing bar system under realistic condition, the test need to be performed using a test setup that could simulate these boundary conditions, which allows splitting of the concrete, concrete cone breakout, and steel yield. Okay, the test method I'm referring here is the test method in pre-qualification stage. Okay, the new rebar model covered in AFAC Technical Note Volume 2, Technical Note 8 Volume 2 includes all those requirements. Okay, so in summary, these are the limitations of current rebar model. Okay, one of the important limitations I haven't covered so far is the type of connection we can be designed using the current rebar model. The current model can only be used to design the simply supported connections. It cannot be used for the moment resisting connection, and all other limitations I have already explained them in my previous slides. So to address all these limitations, we have now a new rebar model that can be used to design the moment resisting concrete to concrete connection. Okay, some of the example of the connections that can be designed using the new rebar model is shown in the screen. Okay, this could be column to foundation, moment resisting connection, or wall to foundation, slab to wall, and so on. So in the images there, the light gray is the existing element and dark gray color represents the new element being connected to the existing one. There are still some limitations in minimum and maximum rebar size or embedment depth in this design model, and all those models limitations are given in ETA or the pre-qualification report, not similar to AS3600. The new design model is presented in detail in recently published AFAC Technical Note 8 Volume 2. Okay, this document is freely available to download from AFAC website, afac.org.au under resources page. Similar to Volume 1, the design method is limited to static and quasi-static loadings. If your application requires other loading conditions such as seismic and others, There are other pre-qualification and the design method available. It is recommended to contact fastener supplier or manufacturer if you have application that is outside the volume 2 of the technical note. The design procedure presented in that technical note is applicable to the post-installed Rebar system assessed as per EAD 332402 and have valid ETA. Okay, so as I mentioned earlier, the shear transfer through shear friction between the existing and new reinforced concrete elements should be ensured by some other means, as rebar doesn't take shear load. Okay, some other means could be the surface roughening prior to casting the new member against the existing concrete. So to design the post-install reinforcing bar connections using the new rebar model, the design principle and procedures are similar to the current process we have in AS 5216-2021. The design action effect needs to be smaller or equal to the design capacity. The design capacities are calculated from the characteristics values of the resistances similar to AS5216 and the capacity reduction factors. There are a few additional capacity reduction factors in this design model, and they are presented in AFAC Technical Note 8, Volume 2, and some of the parameters are already listed in the current version of AS5216. And most of the values and parameters are also reported in the pre-qualification reports such as ETA. So the major differences in this new rebar model is the way how we calculate characteristics capacity of a post-install reinforcing bar. If you remember, in the current model, there is only one possible failure mode, still failure. And other failure mode is avoided by having a large embedment depth or the large cover or something similar. But in this new anchor design theory, there are other possible failure modes available. Okay? As you can see in the screen, the resistance is calculated from 3 different failure modes, and the minimum of the resistance will be the resistance of the post-install reinforcing bar. Unlike a current rebar model, the new rebar model considers 3 failure modes. The first one is rebar yielding, which is there in the current model as well. Concrete cone, this is not covered by the current rebar model, and bond splitting failure, which is again not covered by the current design model. Okay, the combined pull-out and concrete breakout resistance is also covered in the bond splitting model. That include some geometric parameter that is not covered in AS5216, such as the small edge distance or the smaller spacing between different rebars, as well as the anchorage length that is higher than 20 times the nominal diameter of the rebar. Okay, 3 failure modes. First one is, I think, straightforward and very accurately predictable behavior. The steel failure, steel rupture of the post-install reinforcing bar. It is determined by the geometric parameter such as cross-sectional area of the rebar and the yield strength of rebar. Okay, so if you know those 2 parameters, which you do, you can calculate the characteristics steel failure capacity of the connection. So even if there are multiple failure mode shown in the previous slide, it is recommended to have this kind of failure mode in the design of post-install rebar connections, because this is very predictable and ductile failure and has few advantages over other possible failure modes. Second one, concrete cone failure. If you are familiar with AS5216 and you are familiar with concrete cone design model we have in chapter 6 of AS5216, this shouldn't be new for you. Okay, this is exactly similar to the anchor model we have in AS5216-2021. Okay, so the tensile capacity and RKC is determined from the reference characteristic capacity and nut RKC, and there are 4 or 5 other parameters. The reference capacity and nut RKC, this concrete cone capacity of the single fasteners without any disturbance, is calculated using the very popular concrete cone formula K1 square root of FCK FC prime LB to to the power 1.5. The only difference here is we have HEF in AS5216. In new Rebar model, we use LB as an embedded depth of the fastness. And other parameter similar to that presented in AS5216. The only difference we have here is the limitations in the configuration of the fasteners that is given in AS5216 are not applicable in designing of a post-install reinforcing bar connection. This is because they are not designed to take a shear force, and the plane section remain plane principle, or the rigid base plate assumption is automatically satisfied if you are connecting one member to the another designed according to AS3600. And this is the new concept we have in anchorage design. We don't have this bond splitting failure in AS5216. Okay? In this model, the bond slip behavior is considered to address that bond slip behavior I introduced earlier. The bond slip behavior or the concept is taken from the model code 2010, and some of the parameter or the core fitting parameter for that model code bond slip behavior is determined from the testing. So as I mentioned earlier, there are a number of tests obtained, a number of tests conducted to obtain those parameter, and most of the tests are unconfined tests that allows concrete related failure as well. As you can see in the screen, there are a few parameters which is highlighted in gray. They are determined from the ETA, the pre-qualification test we conduct to assess their performance. And a few parameters for the bone slip behavior are determined from the model codes. The highlighted in greens are determined from the model code 2010. That addresses the effect of transverse reinforcement or the confinement of the confinement provided by the transverse and the stirrups kind of thing. And also that addresses the effect of cracking, in this case 0.3 mil cracks in the bone slip behavior. And the other parameter which is not highlighted are the project specific requirement and can be safely used to calculate or to determine the bond splitting capacity of the post-install reinforcing bar connections. And there are some limitations as well. Minimum anchorage length, maximum anchorage length, which can be found in AFAC technical note at volume 2. And this is the summary of the model we have in Australia at the moment. We have anchor theory, Rebar theory, old, and Rebar theory new. I'm not going into the detail because Baz has already summarized some of them in his presentations. This table is a little bit detailed compared to the table you saw, and you can clearly see that they are self-explanatory. And we can discuss them if there are any confusion there. And final few things I want to highlight. The different EADs, specifically there are 3 EADs for the pre-qualification of post-install chemical anchors for the reinforcing bar. Okay, the first one in your left is EAD 330499. This one is for the anchor model. And this includes the pre-qualification of chemical fasteners with threaded rod or rebar as anchoring element. This EAD covers the rebar up to 20 times the nominal embedment depth. Okay, if your application is longer than 20 times the embedment depth, you have the second and third EAD, which is EAD 330087 and 332402. Okay, the first EAD is for the old Rebar model, which we have in AS5216, and second EAD is for the Rebar model new. Okay, this is covered in AFAC Technical Note 8, Volume 2. Accordingly, the pre-qualification report, such as ETA, are produced are different depending on the EAD you are using. The EAD issued or ETA issued in accordance with EAD 330499 is used in anchor model, and the EAD 330087 and EAD 332402 The ETA issued according to those EADs are used for rebar model. The previous one is for the old, the later one is for the new rebar. Please do not get confused with the multiple ETAs. Generally, some chemical products have 2 or even 3 ETAs. Okay, one for the chemical fasteners, shallow embedded, one for the old rebar model, and one for the new rebar model. Okay, as you can see in the screen, these are 2 ETAs for same product. Okay, so depending on which model you are using, you need to use the ETA issued accordingly for that application. Okay, so I would like to conclude my presentation with the slide you have already seen for the post-install reinforcing bar connections. The pre-qualification is done in accordance with Appendix A of AS5216 for the post-install reinforcing bar. Appendix A refers to EAD 330087 if you are using the old rebar model, and EAD 332402 if you are using the new rebar model. The design of a post-install reinforcing bar can be done in accordance with AS5216 Appendix D or AFAC Technical Note Volume 2, depending upon the pre-qualification report you have for the particular PIR system you are using. And finally, the installation. The installation in accordance with manufacturer installation instruction is crucial to achieve the desired performance. For post-installed rebar connection, the required hole depth may be large, and hence the installation quality is extremely important. The installation must be carried out in accordance with the manufacturer installation instructions. The installation should only be performed by competent personnel who know what he is doing. We recommend installer should be trained to install such anchors, either certified by AFAC or trained by anchor supplier or manufacturer for specific applications. That's all I have for you today. Thank you very much for your time and attention. And if you have further questions, we'll discuss them later. Or if you want to contact me, you can see my contact detail in the screen. Thank you very much.
Thank you, Tilak, for your insights. Our audience's turn to get involved. So please ask our speakers your questions via the chat box, and don't forget to let me know who your question is directed to. A big thank you to everyone who has submitted questions while registering for today's webinar. So what I might do is actually kick off with a couple of those questions. So the first question actually will be directed to you, Baz. And this question's come through from Anthony Carey from Queensland. And his question is, the availability of drill bits that can achieve long embedment lengths necessary for lapping bars?
Yeah, thank you very much for the question, Anthony. I reckon it's a good question to be addressed by a supplier. So look, first of all, yes, most suppliers would have standard drill bits available for drilling holes. Some of them definitely carry longer drill bits as well. However, every now and then we encounter situations and applications where we have an extreme deep embedment depth. And that's why your question is very valid, because those drill bits might not be readily available from the supplier stores. So in this case, obviously they have to be ordered as a special item, which might take weeks or sometimes multiple weeks. So my advice would be, I'm not sure if you are aware, but many suppliers are actually offering extension shafts for drill bits. So some of the drill bits can be actually extended. All you need beside the extension shaft is obviously an adapter. Usually this solution works for drill bit diameters at least 32 mil, because 32 or 35 mil would be the diameter of the extension adapter. So obviously you need a hole size which can accommodate that. So sometimes it's possible actually to extend your hammer drill bits, or an alternative way of achieving deeper embedments would be to use diamond coring. Now this is where you probably need the approval of the design engineer as well. Diamond coring changes the conditions in the hole, and not all chemicals can basically safely accommodate that. But there are solutions. Let's say after diamond coring, the holes can be roughened, and you can achieve the originally specified bond strengths with certain chemicals. But this is definitely a topic where the design engineer shall be involved. I hope that answers your question.
Thanks, Baz. I might direct the next question to you again, Baz, and this one's come through from Renato. And his question is there any impact on cost with this innovation, and by how much in percentage?
So if I get it correctly, the question is around if this innovation is going to cost or result in extra costs for the industry.
I think so.
Look, the good news is that I think it's going to result in quite of the opposite. And that's because bringing in this new design method, if you paid attention during especially Tilak's presentation, you heard about how this new design method could potentially reduce the necessary anchorage lengths or embedment depth, and also provide solutions where otherwise or in the past with the current design methods there was no solution possible or achievable. So I reckon in terms of costs, this is actually going to reduce the potential costs or the building costs, because first of all, you can very probably shorten your embedment depth. Secondly, you can use post-installed anchors where they weren't a viable option before. Just to give you a contrasting example, so when post-installed anchors are not a viable option, very often some of the concrete structure has to be demolished and the new concrete structure built, and obviously rebar to rebar connections and new concrete poured, which is obviously going to be a much more expensive exercise. So all in all, I think that the new method definitely has some cost benefits for the industry. In terms of, again, speaking as a supplier, most of the big suppliers have a fixed R&D budget. So from the supplier perspective, even if we are getting our chemicals approved, let's say we are extending our current technical approvals and we want to be compliant with this new design method, I doubt that any supplier would pass on those costs to the clients or to the customers. As I said, usually we operate on a fixed innovation cost every year, and this is not passed on to the customers. In the current market environment, it's probably important to mention that yes, we are seeing some necessary price increases everywhere in the industry, but these price increases are mainly related to other reasons and not innovation. Let's say price increase because of the lack of available materials or the increase of raw material prices. And obviously, living in Australia, it's probably not a surprise that our currency recently weakened compared to overseas currencies. So that might result in some price rise. But all in all, to answer your question, I don't think that this innovation is going to result in any increase in costs. Quite the contrary.
Awesome. Thanks for that, Baz. Tuak, I've got a question which has come through for yourself, and it's from Brooks Smith. And the question is, how does the EU assessment and design guidelines compare to the US ACI?
No, thank you for the questions. Fortunately, they are similar in Australia, Europe, and America. They use a different standard though. For example, in Europe, they design using the Eurocode 2 Part 4 for the anchorage. In USA, they use ACI 318, but the underlying principle is exactly the same. So if you talk about the PIR connections, they are not fully included in the European and the American standard yet, especially the new Rebar model. The number you calculate using different standard could be slightly different because AS 3600 or Eurocode 2 and ACI 318 are not exactly same. But the design principle, design concept, pre-qualification requirement, pre-qualification procedure, they are very much similar.
Excellent. Thank you. Baz, I've got a question for you. It's coming from Stephen, who's watching live. So big hello to Stephen today. And his question is, what is the acceptable tolerance of drilled hole versus the diameter of the anchor rebar?
Such a great question. Thank you for that, Stephen, and thank you for joining us live on YouTube as well. Look, probably I should have clarified this when I wrote up the definition of post-installed rebar. So you're absolutely right that you probably are aware of applications in the past where there were large boreholes created in the concrete. A bar was placed into this hole, and then some sort of epoxy grout or any similar grouting product would have been poured around the bar itself. So that's what we refer to as grouting application. In this case, the boreholes were typically large in diameter, let's say at least 50% larger than the diameter of the bar itself. So just to give you an example, just simplify it to a 10 millimeter rebar, the grouting application would have involved at least a 15 mil diameter hole, or typically much larger than that. The rebarring applications we are addressing here today in this webinar are not the grouted applications. These are post-installed rebar using pre-qualified chemical epoxies. And in this case, you will see that as per the technical approvals, the diameter of the hole is usually only 20, let's say 30, maximum 30% larger than the diameter of the bar. So going back to the 10 mil bar example, you have a 10 mil rebar. Typically, the hole diameter would be 12 mil or maybe 13 mil. And there is a very important reason why we keep it so. If you think about the materials used to create a post-installed rebar connection, these are usually some sort of polymers. And with polymers, if you put them under sustained load, it really depends on the materials used, but some polymers are more prone to long-term creep, which means long-term displacements under sustained load. And this is definitely what we want to avoid. Now, chemical anchors have come a very, very long way over the years. And most chemical anchors that you can find on the market nowadays, they are somehow assessed against sustained loads and the long-term negative effects of creep. So they must have a very good creep resistance. And this is true until you keep that clearance gap, the annular gap between the bar and the concrete small. Once you start to increase the gap, you might run into issues in terms of creeping and long-term resistance of the bars. So this is the very important reason why we want to keep that clearance hole small around the anchors, and we want to limit the amount of chemical within the borehole. So all the post-installed rebar applications that we address today, the hole size wouldn't be larger than, let's say, an extra 20 or 30% compared to the rebar size. I hope that answers the question.
Thanks, Baz. Tilak, I've got a question which has come through from Andrew Deckers. So big hello to Andrew watching live today. How has the longevity of the chemical bond strength been confirmed? And how can we have confidence that the bond will not break down over time?
Thank you. Again, another great questions about the chemical anchors. There has been lots of study on this area, and there are multiple ways they address that while the pre-qualification. Okay, during my presentation, I talked about the pre-qualification design and installation. So your concern is addressed in the pre-qualification stage. So if your application involves the sustained loading, the continuous loading on the anchor, this anchor has to be tested and proven that it will work under those sustained or continuous loading. Okay, so depending on the service life of the structure, the test could last up to half an year, 3 months to 6 months, and it has to show some consistent performance during that time. And they have some mathematical model to predict the behavior after 50 years or 100 years or 125 years, whatever is your design life of the structure. So it has been tested. It has been proved that it wouldn't affect any negative behavior due to the sustained loading. And to further address that, we have a factor in design process we call SISUS, the sustained loading factor, and that will address the reduction in the capacity. and to make sure that it wouldn't fail due to the sustain or the continuous tensile loading during the lifetime of the anchor.
Excellent, thank you. Well,
If
Tilak, actually,
I'm
sorry.
not sure if I may chip in.
Of
Um,
course.
so, sorry, Megan, just I thought I have some extra comments. Tilak has provided a great answer here, just a couple of extra thoughts. This is actually a really important question, the durability of bonded anchors. We are working in various projects. Some of the projects have 50-year intended design life, whereas other projects, especially infrastructure projects, might involve 100-year, sometimes even 120 years design life. And I reckon it's a very valid and very true sort of expectation that these chemicals would perform well throughout the expected design life. So a big change in the industry, which happened over the past decade, that the approval bodies extended the approval scheme, as Tilak has mentioned, and now there are specialized ETA approvals available, which are actually acknowledged by our local Australian standard, AS5216. So my practical recommendation would be, if a designer, specifier, or even contractor is concerned about the design life of a, let's say, chemical epoxy product, then definitely look for those third-party ETA approvals, which are verifying the anchor performance for 100 years or even 120 years. So that should be made available by the supplier themselves, and it should be given for free to the client. So these approvals are out there, and please just look for a product which actually has been pre-qualified for these extended design lives. Just a quick comment. Thank you.
Perfect. Well, Baz, while you're speaking, I'll ask the next question to yourself. A question's come in: how much reduction or increase in capacity if the anchor is in tension or in compression zone of the concrete material?
Okay, that's a good question. The answer would be it depends. So this is related to, I suppose, the design of post-installed reinforcing bars. As we mentioned throughout the webinar, yes, it makes a difference whether we can anchor into the compression member or when we cannot. And the main difference would be that usually in the compression member, we don't have to expect the formation of the concrete cone failure, which is a brittle failure, and it's obviously not a favorable failure mode. So we want to avoid the brittle concrete breakout. In the compression member, we can most often achieve that. What happens if we cannot anchor into the compression member though? This is where we very probably have to use a design method which actually accounts for the development of the concrete cone, and we have to check how much the resistance would be reduced. And this depends on many factors. This is why I said that this is actually a very complex question, because depends on the embedment depth, depends on how we can transfer the stresses. Can we transfer the stresses to an existing bar? Let's say, can we do a lap splicing inside the concrete? If not, and we are not in the compression member, then the concrete cone failure becomes a very valid probability, and we have to check for that. And if we want to avoid it, or if we want to increase the anchor resistance against the cone breakout, then the best thing to do is probably, if we can, go in deeper, or maybe supplementary reinforcement, if we can check the existing reinforcement around the fixing area. This is not exactly the same as splicing with an existing rebar, but here we are checking if there is adequate reinforcement in the concrete member engaged within the size of the concrete cone, so hindering the breakout of the concrete cone. So there are a couple of tricks we can do, but most often we expect a certain drop in the achievable anchor resistance, and that's because of the probability of the cone failure. So anchoring into the compression zone, always better. If not, then we have to check for the possibility of the cone failure, and we might be able to adjust the design, but very probably we will have to change something in the design to achieve a better resistance there.
Oh, thank you, Baz.
Yeah, I can add more to the
Yep.
Buzz response because Buzz has covered most of the thing. There are a few other parameters we consider. For example, if you look at the cone failure, Buzz had addressed very well. There are a few factors that are different for concrete that is in compression, and there are different factors for concrete that is in tension. For example, If the concrete is in compression, there will be no possibility of cracking, so we can use the on-crack concrete in designing. For example, if you're using the post-install rebar connections, there is a factor called psi MN factor, so that considers the effect of compression force from the moment, for example, that will always increase the concrete cone capacity. Okay, that depends again on several parameters. For example, how far the anchor is from the edge, and what is the lever arm, how much the percentage of the compression force due to bending compared to tensile force. There are a few factors you need to consider, but again, as Baz mentioned, it's definitely beneficial to have the anchor in compression zone where you can utilize the better confinement, and it will definitely produce the higher capacity of the connection.
Excellent. Thank you, Tulak. Well, Tulak, we've got a question which came through from Rob Steele, who's watching live. And his question was, to provide confinement for control of concrete splitting, is fibercrete effective?
Yes, we hope so, Rob, but we don't know how much it would help. So it's under investigations. The different research team around the world are working on that. And we in Swinburne University are doing series of experiment using fiber reinforced concrete. We have seen some promising result from the early stage of testing, but we will be able to answer this question in detail maybe in the future webinar or future seminar once we get the very much detailed result from the experiment.
Excellent. And while I've got you chatting, I've got another question from Shantana, and their question was, is there any minimum value for rebar embedded depth?
Yes, there are. It depends on what type of design model you are using. We introduced a 3 model in today's presentation. The first one is the anchor model, where the minimum embedment depth needs to be 40 mil or 4 times the diameter of the rebar. And if you are using the old rebar theory or whatever we have in AS 5216, the minimum embedment depth needs to be in line with AS 3600 requirement. And again, if you are using the new rebar model, which I introduced, the minimum embedment depth needs to be taken from the pre-qualification report, which is usually the maximum of 30% of the development length determined from AS 3600 or 100 mil, or there is one more parameter, 10 times the diameter of the rebar. So it has to be maximum of those 3. Again, depends on the type of model, type of design model you are using. And usually these values are listed in the pre-qualification report or ETA.
Excellent. Thank you, Tulak. Baz, I'll bring you back in to the conversation. We had a question which has come through from Ian. And the question was, for post-installed rebar, holes are usually quite smooth-sided. How can designers be sure that the bond with the concrete element be achieved?
Yeah, so that question is obviously concerned about the hole conditions on site. And here I would probably distinguish between various drilling methods. Obviously, with the traditional hammer drilling, we always expect a certain level of roughness within the borehole. However, as I mentioned in a previous comment, there are some drilling methods, for example, diamond coring, which result in a very smooth finish. And then it will definitely affect the pull-out resistance, the bond strengths of the fixing, which has to be accounted for during the design. Ian is asking how we can make sure that the right bond resistance is achieved. One potential way, if we don't have any information what happened on the site, then there is still some, I would call it an extra line of defense. You can still specify on-site proof load testing. This is different to the pre-qualification tests, and this is different to destructive testing. But let's say you designed a post-install rebar connection, and your goal was to achieve full development of the bar, to achieve full bond strength, full steel capacity of the bar. Then you could still specify an on-site proof load test, let's say up to 90% of the expected yield strength of the bar. This would probably not cause any issues or any damage to the already installed bars on site, but it would be a very effective way of figuring out whether the installation happened as per the manufacturer's installation instructions or as you specified. So on-site proof load testing is definitely one practice. Just for your information, I can tell you some extreme examples that we see globally as well. I take you to Singapore, for example, where it's becoming a common practice that the installer would have a side camera or a webcam when they do the installation, and the designer is actually observing the installation or watch it retrospectively. So we see some really extreme examples as well as trying to control what actually happens on the job site. Obviously, the quality of installation is a very important factor. Usually, we like to implement various defense mechanisms to avoid any potential issues with these post-installed anchors or rebars, and one would be making sure that the installer is actually qualified and they have a correct understanding of what they are doing. I'm not sure if you're aware, a bit of advertisement to TILEX organization AFAC. AFAC actually has a very good and very comprehensive installer certification program in Australia. Some of the road and transport authorities are already mandating this installer certification. For example, in Victoria, on Vic Roads job sites, it's a mandatory requirement for the installers of bodied anchors to go through the AFAC certification. This is something, again, I believe a designer could prescribe or specify that the installer must be trained by AFAC or the anchor supplier. And then, as probably the last line of defense, what I mentioned earlier, on-site proof load testing would definitely identify any potential errors or mistakes made during the installation.
Excellent. Thanks, Baz. Well, I've got another question for you, Baz, and it's from Mike. And his question is, how do we make sure the surface roughening is taking all of the shear? Are there guidelines on the level of surface roughening to achieve the equivalent of monolithic concrete?
Mm-hmm. Yeah. This question is a little bit similar to the previous one, but if I get it correctly, it's not related to what's happening inside the hole, but it's between the old and the new concrete, so on the interface. We mentioned in our presentation that in classic and traditional reinforced concrete theory, we don't directly place shear force on the reinforcement. We like to utilize the reinforcement in tension, more or less. So in this case, the shear force between new and old concrete should be transferred via a rough interface. And a very good question, how can we make sure that we have adequate roughness? How do we specify the roughening of the interface? And I have to admit that AS 3600 doesn't really elaborate on that topic too much. But luckily enough, we've got some good international guidelines. And maybe I would encourage you to check out the European design methods, especially Eurocode 2 Part 1. Eurocode 2 Part 1 has a dedicated chapter to understand the shear transfer between concrete elements that were poured or installed at different times. And this section in Eurocode 2 Part 1 will actually give you different levels of roughness. It will define what is smooth, what is slightly rough, roughened, and indented. And it actually provides definitions for that. So for example, we usually say that we want to definitely have a adequate roughness between old concrete and new in order to transfer the shear stresses. This is actually clearly defined within Eurocode 2. And it will give you some examples how far the aggregates should protrude on the existing concrete surface after the roughening. And from top of my head, it has some sort of definition, let's say 3-4 millimeter increments at every 40 or 30 millimeter distance. So it will provide you with a clear definition if you're interested in that. So in summary, I reckon probably the best guideline for this topic would be Eurocode 2 Part 1.
Excellent. Thank you, Baz. So, like, I've got a question which has come through from Ferry, and their question is, what is the minimum edge distance to concrete required for post-installed rebar to prevent splitting failure?
It depends on, again, which type of design model you are using. Again, if you are using the current rebar model we have in AS5216, the edge distance and cover and everything will be from the AS3600. So our aim is to have a development length, and we want to have a steel failure before any other concrete related failure happens. So all the requirement to get that development length from AS3600 needs to be followed. If you are using the new theory I introduced in my presentation, then these are product specific. So I cannot tell you exact number. And these has to be determined from the testing, the pre-qualification testing. So all those requirements, all those numbers and limitations are given in the pre-qualification report, such as ETA. So it's good to go through the ETA pre-qualification report and follow them accordingly. They are product specific and the product dependent.
Thank you. So, like, there was another question which has come through live, and if the edge distance available is not sufficient, then can we offset this by increasing the embedment depth, assuming that it will be less than 20?
I think the three parameter I introduced. If you do that, it will violate that principle. I mean, you have to test, or you have to provide the proof that your anchor would work in the condition you are using. Because if your application has been considered during the pre-qualification testing, yes, you can use that product for your application. But if the application is outside that scope, then either you have to do the test to prove that this application works. Otherwise, try to find some other product that has that scope within that range. So again, if the application is outside the scope of the design method or outside the scope of the ETA or the pre-qualification report, I wouldn't recommend doing modification and do one to compromise other thing. It's better to stick within the scope. If not sure, do the testing or talk to the manufacturer. They might have done testing or they might have better recommendation to you.
Thank you, Tilak. Look, I think we're actually running out of time. So, Baz, I might direct the last question to yourself. And that's come through from Rob. His question was, does Hilti provide ETA prequels for its products?
Thank you, Megan, and thanks, Rob, for asking the question. ETA pre-qualification documents, I believe the question is. Yes, of course. So if you visit the Hilti website, hilti.com.au, and you search on the product that you're interested in, one very typical product would be the RE500 chemical family for post-installed rebar applications. Under the Documents and Downloads tab, you would find a series of ETA approvals. And hopefully the purpose of today's webinar helped to understand why we actually do have multiple ETA approvals. It really depends on the application, depending on whether we design the post-installed rebar as an anchor. This is usually the shear applications when we place shear force directly onto the bar, then we have to design it as an anchor. Hilti would have the anchor ETA for this product. Then if you wish to design the product in accordance with AS3600, then we would have an ETA dedicated for that design methodology. And the new design method that Tilak presented here today, we already have the ETA approval uploaded for that as well. Just one more comment, perhaps, because based on the questions, you can probably feel and sense that there is a large complexity involved in the design of post-installed anchors and post-installed rebar. I would also encourage you to probably utilize the existing design software available by multiple suppliers, including Hilti. We offer dedicated design software for the purpose of post-installed anchor and post-installed rebar. So please get in touch with us and we can definitely help you setting up the design software or even demoing how the software works, because I reckon it just makes the entire process significantly simpler.
Perfect. Thank you, Baz. Well, look, that's all the time that we have for today. So please join me in once again thanking our speakers, Baz Kaknix and Tilak Pokral, for their time and input. I would like to thank Engineers Australia's industry partner Hilti for their support with today's webinar. And a friendly reminder to everyone that Engineers Australia's flagship event, the Climate Smart Engineering Conference, is scheduled for the end of this month, the 29th and 30th of November. We encourage you all to please visit our website and to strongly consider attending, as engineers are poised to offer numerous solutions to address these impending challenges that we face. And if I could also ask for everyone to please complete the short feedback form, which is linked in the description box below. We really do appreciate the time it takes for you to do it, only a minute or two, but giving us that feedback does help us improve and plan our future sessions. And finally, thank you again for joining us, and we hope to see you at our next Thought Leaders event. Good afternoon.